And for roof and ground mount systems, we want to have a low solar panel that's able to adjust its angle to track the sun as though it's a pole mount system. So this will allow us to be sturdy during heavy weather. We're able to track the sun and possibly extend the amount of time that we can pull solar energy. In our particular region, we could possibly increase it from 5.5 hours to 6, maybe 6.5 hours. Whereas with the extremes of angle rotation.
So here's some history on the solar market. The United States installed 1,000, almost 400 megawatts of solar photovoltaics in the second quarter of 2015. That's enough capacity to almost power 5 million homes. So the residential market is also breaking records with a 70% growth year to year. Throughout the first half of 2015, 40% of all the new electrical generation capacity was brought online from solar panels. The SEIA, the Solar Energy Industries Association, forecasts that the photovoltaic installations will reach 7.7 gigawatts in 2015, and that's up 24% from 2014. So here you can see installation of solar panels. This is 2010 on the left, 2015 on the right, and for residential, non-residential, there's an increase across the board for all aspects of solar panels. And same thing with pricing. It's kind of like a supply and demand classic case. As the industry is scaling and becoming more popular, the prices is falling. So that creates a lot of incentive for people to go solar and help reduce costs. Some of the main players in competition, Trina Solar and Tingly Green Energy. These are Chinese companies and they dominate the manufacturing business of solar panels in China. Canadian Solar, they're based in Canada, but most of their manufacturing is done in China. And then First Solar and SunPower are two of the biggest American solar panel makers that we have here in the United States. So why is our project better than what's out there already? Ours is different because most solar panels that follow the track the sun will be on like a pole mount that go vertical like this, but we're going to have our mount be for flat roofs only. So it's going to maximize electrical output. We're going to have sensors that track the sun, as they mentioned earlier. It's going to be easy installation. That's going to be one of our key points. We're going to market towards the customers, telling them that it's not going to be a complicated process. We're going to make it easy for you. And introducing clean energy is also a benefit for people to go solar. So some of the marketing requirements, we want to reduce electric bills because cost is one of the biggest reasons why people are afraid to go solar. They don't think that it'll benefit them in the long run. We want to offer a range of financial options so the customers can finance solar panels if they don't have the money up front or something like that. We want to educate the consumers on why solar is the way to go and how it could help them in the long run. We're going to make sure they have more efficient output. We want to raise the level of visibility of solar in the marketplace, keep solar in mind. Again, easily installation and setup, and we're reducing the complexity of going solar. Here's some existing projects that people have already been working on. U.S. Army, they have a patent for developing a tiny photovoltaic solar cell. It's like really, really small compared to what they have already in the market. Apple, they have a patent which they basically want to have their cell phones have a solar array embedded into their design so that they can have self-powering mobile phones, that would be really cool. Colorado, they have a Grand Valley Power company which they developed a 24 kilowatt community, and they basically use that solar farm to help low-income people reduce their bills. Canadian Solar, they created a new line of integrated solar panels which offer grid-ready three-phase inverter integration. Some of the alternative approaches that we decided to not go with were optic sensors. We're going to end up using LDR, light-dependent resistor sensors, which are cheaper, and they ended up being better for our project. we're going to use a rectangular support frame. Like I said earlier, it's going to be for roofs, like a flat design, not a pole mount. And we decided that we're going to have a main support beam in the center of our rectangle that will basically support most of the weight of the panel, because we don't want anything breaking. So we're going to have, we decided to make it a pivot so that it can, adjust the movement of the panel. And yeah, that's it.
So these are the needs identification part, and so this client request is more of a general client request, and these are just some questions that you would ask to help break down the problem and get at a better solution. So, such as what is the current spending of energy, and this would just give us a average value for the daily, monthly, or even yearly cost, and so then from that we can determine percentage-wise how much power we should provide them with in relation to how much they actually draw for the whole year. And it would be percentage-wise because financially speaking, it's not viable to cover the entire cost, because that would mean a huge upfront cost, and maybe that's not something they can do right up front. Another one is during what hours of the day is energy consumption the greatest. It just gives us an idea of the peak value. So again, so we can implement it into our final design. Third one is, will there be an increased number of equipment within the year? This question isn't necessary, but it just, maybe if they want to take into account what any future power consumption that they might add, but again, it's not necessary. These are the marketing requirements, and these are also general, because depending on what specifically the company has for power requirements, then we would change them. But these are general, and you can see that there are reduced energy costs. So implementation of the solar panels should result in reduced energy bills. The system must allow for normal operation without interrupts. So long as the solar panels receive a specific amount of solar energy or light, they should continue to operate, and it should not affect the overall operation of the equipment that the company operates. The system should be reliable, so this just adds to the second bullet. The system should need no maintenance or very minimal, so you shouldn't have to tamper with it or fix or repair anything on it. It should just operate right as soon as you install it into your system. The system should be non-obstructive, so wherever this is being implemented, whether it's on the roof or on the ground, it should not impede with the workflow of the employees. System should be durable, so so this will be the stress test. So under changing weather conditions, the system should remain intact and continue to operate as functionally as it can, given the changes. This is just a hierarchical relationship of all the criteria and the sub-criteria. And this is the pairwise matrix comparison of the criteria. So you can see the first one is just the top level criteria, and then as you go to the bottom 30, you see the top level criteria. You see the individual comparison of just the sub-level criteria to itself. Thanks. And these are the three alternatives that we came up with. So rotation by one motor, two motors, and actuators. Rotation by one motor, it's just a rotation along one axis, so it would be tracking along the east to west throughout the day. Rotation by two motors is two axes, and so it would be tracking along east to west throughout the day and north to south throughout the seasons. Actuators, they function similar. They are also two axes, but function somewhat differently than rotation by two motors, because now it's four, and so you'd have one here, one here, one here, one here, and so they move around to manipulate the surface of the panel, so it would face wherever along it.
So this is the alternative actuator hydraulic system. Due to the fact that we have calculated that a small scale system will be good for HRC, we're going to be using a rack and gear system to be doing that to simulate the hydraulic system. Major obstacles need to be overcome would be strong and light framework to be provided, so we can actually wrap mount on the roof without being too heavy. Because as soon as you start throwing 3 tons on a roof, things start kind of falling apart. And we are going to basically make an easy installation for the client and an easy use interface for programming. Project summary, we kind of really hit on a lot of slides, but basically making a solar panel that's easy to install, to use, and having it be relatively maintenance-free and self-reliant. Our system design description here, I broke into subsystems. We're going to have the embedded controller, the Bluetooth module, the DC motors, a power supply board that converts powers based on board requirements, power meter, solar tracking module, and an Android smartphone. For our embedded controller, we're going to use a Raspberry Pi 2 because that provides us with an operating system already pre-installed on a small computer. This is basically provide a very efficient embedded controller because we can implement complex algorithms due to the high processing speeds, and we can store a large amount of data within its memory. It requires a 5-volt, 1200 milliamp power supply and power from the power support, and will directly interface with the Bluetooth module, power meter, and hydraulic motors. For our Bluetooth module, we're going to be using a Bluetooth WT41A. It's a long-range Bluetooth module of a range of 1 kilometer, but due to the fact that smartphones are not, that's only talking itself. The smartphone range should be about 200 feet. It is the interfacing device for Raspberry Pi and an Android phone, due to the fact that Raspberry Pi doesn't have a self-containing Bluetooth module, and will basically just act as a serial relay. It requires custom PCB to manufacture, and requires 3.3 volts and 500 milliamp power supply. Power supply we'll have a rack and gear system to simulate the hydraulic actuators, where due to the fact that in small scales you don't really need hydraulics, but basically an actuator is a stepped up rack and gear system for large scale applications that have an internal casing. A power supply board will be stepped down to 12 to 5 volts or 3.3 volts with proper current output. Needs custom PCB to be manufactured. So basically what will happen is all the solar output will be going to a 12-volt battery system, and this will step down all these voltages and current regulate them so that we don't blow out our electronics. Our solar tracking module will be using light-dependent resistors, as said before by Steve. We'll send in analog information to Raspberry Pi to be processed, so therefore basically have a little bit of A to D conversion going on, and storing that data within its memory to keep track of how the power how long is basically how well it's doing. And it needs custom PCBs to mount sensors and process the raw data. Dependent, well, the power meter, I unfortunately did not make the slide from last, but we have a I found a DC power meter which will basically keep track of the output and efficiency of the solar cell that we're going to be utilizing. An Android smartphone, I'm going to probably be using my own smartphone for this, and we're going to create a general app which will work on version 4.0 or greater. So anyone that has an Android smartphone can install it and program the solar panel mount efficiently and effectively. Over here, we're going over the system behavior charts. Here's basically a position flow chart. Here we start, get analog data from the sensor, we'll store the values in memory, compare it to signal strengths, and basically use that to triangulate the position. If it's facing the sun, we'll do nothing because we already have it facing the sun. And if it's not, we'll compute position adjustment and send controls to the hydraulic motors or the DC motors. Meter flow chart. We'll get analog data from the meter, see what kind of power output becomes, the power that we're getting from the system. We'll compare the signal strength, store values in memory. Basically, send the data to a Bluetooth module. If there's a request from data from the Android phone for updated power analytics, because we're going to have the ability to, for the Android phone to connect to the Raspberry Pi system to see if we can get how much power we're actually recording. So this will basically be stored in the Raspberry Pi, And if there's a request, we'll send some Bluetooth module and be relayed to the Android phone. The Android control and data flow. We're going to actually have a backup system to this in the Raspberry Pi. We're going to store internal geolocation data and sun position data. So basically, when it's at 7 o'clock, 8 o'clock at night after sunset, the and the solar panel is facing the completely wrong way, we're going to have this Raspberry Pi and go, okay, it's sunrise is at this time, face this general direction for the sun position. So it basically acts as a reset mechanism and increases the accuracy and location. So basically, we have a two dual comparisons based on the sensors and the geolocation. The way this works is that we pull this off of NOAA's website, send them geolocation data based on Android smartphone GPS locations, send it to Bluetooth letter related data, process the Raspberry Pi, and store the data in configuration files.
Okay, so as this project's going on, and there's a few key things that we want to have done at different points in time. We want to have the algorithm completed before we move on, and we want to make sure that the sensors will operate for what we need. But the biggest thing is the first hardware and software integration test. If we can't get the hardware to actually respond to the algorithms we have, this project might not even be able to get off the ground. But if we are able to keep going, I think all the major milestones we'd like to have would be the Android app sending and receiving data from the solar panel mount, all the hardware communicating simultaneously with our Raspberry Pi. Currently, there are ways to just adjust things slowly so that it can be done asynchronously, but ideally we'd have everything working synchronously. And finally, we'd like to have the system designed so that it's very quick and easy to assemble or disassemble instead of being all a single product that has to be delivered as one piece. So testing flow, there's going to be unit tests, integration tests, acceptance tests as per the requirements for the course. There's the unit tests for software. It's going to be perpetually happening. As each class in the program is developed, we want to test it with the randomly generated data and also specifically generated data. For example, for the solar tracking and actuator movement, feed the actuator there's fake data that would be well beyond their limits and see how the program reacts. So that if we find a bug when it's deployed, the system won't go out of control and end up breaking the solar panel. For the hardware tests, we want to have each component tested individually before we start integrating them to make sure that all the lines are marked correctly, the devices are actually working, and they'll respond to the data that we send out. And when possible, we want to do these tests with embedded boards so that we're working as closely to the real situation as we possibly can. Once we get to the integration testing, for the software,
our DC motors are going to be about $10 each because they're relatively cheap for the scales that we're using and shouldn't be too much. Rack gear system should be $10 each because we're going to probably use a little cheap plastic system that, of course, is not going to be that over expensive. Power meter is going to be about $7 because we're just using DC power. We're not hooking up right into the AC power lines to see how much power usage we're using. Test our Android smartphone will be free due to the fact that we have an Android smartphone. We'll be using that for testing the app and integrating the app. Solar cells should cost about $40 each depending on the size. That's up to the cost. And the estimate total cost will be $212, and we'll probably be spending some of our own personal money to cover extra costs. I have here to update deliverables, which kind of follows along Tim's timeline here from when we actually get into prototyping. As you see here, Steve and I will be working on designing the circuitry, and I'll be working on first parts. Tim and I, since I have a lot of experience with the embedded program, I'll help Tim with the embedded software if he needs it. And Android will be developing the smartphone app on its own. Next, we'll be constructing and building the test circuitry. So we'll be building constructing and all the circuitry that we have together, and Steve and I will be testing these functionalities together. Meanwhile, Tim's and Steve and Andrew's designs will be entering the alpha phase, and they'll be doing initial testing and seeing how and see if they can find as many bugs as possible. From there, we'll actually go to the beta test of the software and actually start integrating the hardware together. So once we get a fully integrated hardware system, we can actually get a really good software test going based on having all the systems talk together and see how they're doing, and hopefully we can finalize the software implementation then and there. From there, we'll develop an actual framework and start integrating the motors and the actual framework design. So we'll do all the